Okay, so we made it. It's my real pleasure to introduce the final speaker for the conference, Professor Andy Hone from the University of Kent, who will talk to us about new cluster algebras from old.
Thank you very much. Thank you very much, Anton, and thank you for the invitation. It's really great to be here in Beijing. It's my first time in BIMSA, but not my first time in China, and it's good to be here again. Okay, so I'm going to tell you about some joint work with a few different people. So the first one was my former postdoc, Theodoros Kouloukas, who's now based in Lincoln in the UK. And then another two collaborators are Jan Grabowski, who's an algebraist in Lancaster, and Woo-Kyung Kim, who is his PhD student, but now also my PhD student, because I started co-supervising him during the pandemic. And then also Takafumi Mase from University of Tokyo. So there's, if you're really interested, there's a paper with Theodoros in Journal of Algebraic Combinatorics from a couple of years ago already. And there's one preprint on the archive with Jan and Woo-Kyung, and another preprint with Woo-Kyung and Mase-san. And Woo-Kyung's thesis, he told me he's going to submit it next week. So there's even more things in his thesis, which probably haven't appeared anywhere yet. But so I'll sort of give you a foretaste of that if I have time. Okay, so what's the main idea of my talk? Just to give you the idea of what it's about. So the main idea is to start with cluster algebras of finite type, and then obtain some new discrete integrable systems, or hopefully new examples of discrete integrable systems. And these discrete integrable systems will turn out to also be related to some sort of interesting families of cluster algebras that naturally come out of this process. So I won't assume that you know anything about cluster algebras or necessarily about discrete integrable systems. My aim is to be very pedagogical, at least for the first half of the talk. But I'm also quite slow at talking, so it may be most of the talk. And then if I have time at the end, I'll try to just show you some of the really slightly more technical results or new results. So I won't assume that you know anything about cluster algebras. I really want to explain some simple things for the most part. And sort of what is the origin of this topic or this project? Well, it's really sort of just one very simple observation about one very simple example, which is more or less the first interesting example of a cluster algebra, which is the finite type cluster algebra associated with A2. So that's what I'm going to spend most of the time explaining A2 and how this deforms in a certain way and produces something integrable. And so that was the basic observation, the basis of the whole idea. And then maybe it was sort of hopeful that just this one example would then generalize to sort of all finite type cases. And well, the evidence is that it does. But I'll try and give you some evidence, try and convince you at the end. Okay, so what is the motivating example? Well, luckily, we've also kind of seen it, or some of its avatars, in various talks actually today. So the motivating example, and what I will spend, as I said, most of the time talking about, is what's called, in some communities, the Linus 5 cycle. So the Linus 5 cycle in dynamical systems, it's a very simple dynamical system defined by a recurrence relation of second order. So the recurrence relation is this one. And this was discovered by a British school teacher called, I think, Robert Linnes in 1942, and a small article called Cycles in the Mathematical Gazette. But then it has many avatars. So some which come from, sorry, spell avatars correctly. So some which come from long before Linnes. So there's Gauss, the pentagramma mirificum, which is looking at pentagram inscribed on a sphere, but then also the pentagon identity for the dilogarithm, which was mentioned in the first talk today. And then, well, there's associahedron, which comes from putting brackets in expressions with 4 variables, which corresponds to the triangulations of the pentagon, which we also saw in the first talk today. So those are some examples. And then there's also, in Volin's talk, it was mentioned also Zamolodchikov periodicity. So that's this is kind of the simplest example of Zamolodchikov periodicity, which I'll just explain in 1 minute. And then, okay, then in cluster algebras, there's the A2 cluster algebra. So I'm not going to explain all of these instances of this recurrence relation, but it just gives you an idea that it appears in many different guises. Oh, so what's the kind of surprising thing about this recurrence relation? Well, if we iterate, so we start with two values, let's say x1 and x2 as our initial values, and then with n equals 2, then the next value we get is x3, and that will be x2 plus 1 over x1. And then if we iterate again, the next value we'll get, x4, will be x1 plus x2 plus 1 over x1 plus x2. And then a kind of miracle happens when you work out x5, because you're adding on 1 to this, and then you have to divide by x3. But in fact, you'll find that this polynomial in the numerator will cancel from the denominator, sorry, this numerator here will cancel from the numerator of x4 plus 1. So then actually what you find is x1 plus 1 over x2. So it kind of gets simpler again. So this is part of the magic of cluster algebras, or the magic of the dilogarithm function, or the magic of the associahedron, or however you want to look at it. And then actually the next step, lo and behold, you get back to, you add 1 to this, you see that this numerator cancels, and so you get back to x1. And then you can also do one more step, and then x7 will be x2. So then you see it's 5 periodic. So xn plus 5 is equal to xn for all n. And this is exactly the simplest case of Zamolodchikov periodicity. So the simplest Y system for A2, the period is the Coxeter number plus 2. So the Coxeter number is 3, 3 plus 2 is 5. So there's the period. So that's the five cycle. All right, so that's sort of something very, very simple, but nevertheless somehow miraculous in its own way. yeah, I guess I should also, another example that I missed, which is sort of somewhere, maybe somewhere about here, is also Coxeter in his work on Frieze patterns. Also, he generated the simplest kind of Frieze patterns from this as well. So he cited Linnaeus as well, and the pentagram, yeah, of Gauss. So okay, so that's our sort of starting example, and so what I want to do, apart from the 5 periodicity, I want to list some properties of this iteration, and some of which are sort of immediately obvious, and then some of them will be sort of look technical, but and maybe unnecessarily technical. But let's see, because then we want to see how they generalize. So I guess again, just to motivate the whole talk. The idea is, the general idea of the talk, if you kind of fall asleep or anything, is that we start off with cluster algebras of finite type, which generate periodic dynamics, and then we deform that in a very controlled way, and we destroy periodicity, but nevertheless we retain integrability in a certain sense. Okay, so this, as a dynamical system, this is somewhat trivial because all of the orbits are periodic with the same period. So if you want to think about integrability, it's sort of trivially integrable. But the main observation is that you can deform this in a very simple way and still retain integrability. And then it turns out that actually there's another cluster structure sitting underneath. Okay, so let me just list some properties. Okay, well, so there's Zamolodchikov periodicity is so properties of the Linnaeus 5 cycle. So the property that we've just talked about is Zamolodchikov periodicity. Another property which is very relevant in the context of cluster algebras is that all of these iterates are Laurent polynomials. So this is what's called the Laurent property. So what does that say? In this case, it says that all of the iterates belong to the ring of Laurent polynomials in the 2 starting values with integer coefficients. Then another trivial, sort of almost trivial property, but if you know about symplectic maps, that this is a symplectic map with almost the canonical symplectic structure, but what's called log canonical. So the 2 form is just dx1 wedge dx2 over x1 x2, and if we think of this as we can think of this as a map. So I think I want to write this. Think of it as a map in the plane. Then this is what it is explicitly as a map, and this 2 form is preserved by the map. So if you have a canonical symplectic map in dynamical systems, the name that's used is sometimes a standard type map. So up to taking logarithm, this is like a standard type map, but you really want to use this log canonical structure. And then, okay, finally, this is actually, but again, this seems rather trivial, but this is an integrable system, a discrete integrable system in the Liouville sense. And this is rather rather trivial. So what does it mean to be a discrete integrable system in this context? Well, you have say you have a symplectic map on a phase space of dimension G. So this was we've seen examples of ordinary Liouville integrability several times in this conference. So we need to have G independent first integrals which are invariant under the map, and they have to be in involution with respect to the Poisson structure. Okay, with respect to the Poisson bracket, they're in involution. So here we have a system with 1 degree of freedom. We only need to have one integral. So it's easy to find an integral for a periodic map. And in fact, there's something rather funny that happens for a periodic map, where in 2 dimensions, in fact, there are 2 functionally independent first integrals for this map. So let me show you how you can see that. So what you can do if you have a periodic map, you can construct integrals by averaging any function over an orbit. So I'll take this function, and what I'll do is I'll take just the function, one of the coordinates, and essentially average it over the period. So here's, let's go 1 to 5. So we see the period is 5. So we just averaged this function over the period. And actually, no, okay, we can do the sum. It's almost identical, but I'm going to average. We can take any symmetric function, if you like, along of a function along the orbit. So actually, I'm going to do the product. Why? Because it's easier to write it. So now you can just see these Laurent polynomials. We can just multiply them together. And so what we get is x1 plus 1, x2 plus 1, x1 plus x2 plus 1 over x1, x2. And that's also a Laurent polynomial because we sort of almost by construction. So then this function is clearly, because of periodicity, this function is invariant under the action of the map. So we have 1 degree of freedom. We only need one function. So it's sort of trivial. But also, you can construct another integral. So, okay, this time I will do a sum. So I'll do the sum from j equals 1 to 5, and I'll do acting on. Now I'll take the product x1, x2, and I'm not going to write it down, but it's some slightly larger formula. Now, so what can you see? Maybe I draw a picture. So okay, so what does this tell you? It tells you that, of course, the orbits lie on level curves for both of these functions. So the level curves of H1, well, if we just now this is a curious fact, because I did a little numerical calculation yesterday. So okay, if we take a level curve, H1 equals constant. I think the one that I did was H1 equals 9. And then there's also the curve H2 equals 17. So let me see, does that work? Maybe not. Let me say 1, 2, no, 12, sorry, there we are, yeah, 12. So if I take the orbit starting from 1, 1, from the point 1, 1, then the value of H1 is 12, 2 times 2 times 3. I think the value of H2 will be 17. You can work that out yourself. Okay, the curve. So the curves, generic level sets of H1 are genus 1 curves. They're elliptic curves, biquadratic curves. I'll come back to that later. The level curves of H2 are genus 6, actually, rather, and they both sort of don't look that different. They have they both have a nice oval in the positive quadrant, and then they have some other disconnected components which I'm not going to try and draw properly. But what's amazing is that for this particular values, at least, well, so actually, what you see is that you see a picture like this. So 1, 2, 3, 1, 2, 3, 4, 5. So here's the 5 cycle. So the thing is that this curve, this oval is tangent to the other one inside in these 5 points. So this is the orbit of the point 1, 1 where you start, and it goes round. But the thing is, I plotted these curves with a computer, and I couldn't see the difference between them by eye. So all I could see was 2 ovals stuck one upon the other. But if you look at resultants and so forth, you can see that these 2 curves are really independent curves. So anyway, this was rather surprising to me. I think it may be something to do with the values of the dilogarithm. There's some identity of Ramanujan that shows values of dilogarithm which are very similar, and that's why these curves almost look identical to the eye. But anyway, that's another story. Okay, so I mean, this is trivial, but in a sense, integrability is trivial, but you even have 2 independent invariants. So what's the main idea of the rest of the story? Well, first of all, just to comment on the cluster algebras, which I'll introduce in more detail in a second. But Zamolodchikov periodicity is something that comes out of cluster algebras in finite type. The Laurent property is a property that's shared by all cluster variables in cluster algebras. The symplectic property here is part of a general pre-symplectic structure which you can construct from a cluster algebra. And then integrability, well, integrability is always special in general. So you can most systems that you can construct from cluster algebras will not be integrable. So integrability is always like some extra feature. And so the main observation here is that this system can be deformed in a simple way, and it will destroy the cluster structure, but it will preserve integrability. So the observation is you can inserting parameters in the Laurent recurrence preserves integrability. So what you can do is this. So this is also known as the Laurent map. You write down exactly the same kind of recurrence relation, except you can put some arbitrary parameters in front of the terms. And then maybe I get a different color. So here's properties of the Laurent 5 cycle, and now let's look at the corresponding properties of the Laurent map and just essentially tick or cross according to whether they hold or not. So Zamolodchikov periodicity, no. So I mean, if you insert these parameters, you no longer get a periodic dynamics. Laurent property, no. You also destroy the Laurent property. But symplectic, well, it's exactly the same standard type with the log canonical form. And so you do preserve the fact that it's symplectic, and also you preserve integrability. But now the function you take, well, this function is the function to look at, actually. So the function you get almost looks the same, but you just need to insert A and B in appropriate places. So this family of curves of genus 1, for the level curves of genus 1, this is what generalizes. This other thing doesn't generalize in that case. Okay, I mean, you couldn't have another integral in general for an integrable system. Okay, so that's very, unless it's periodic. Okay. So this is the idea, but also, in fact, it also has a hidden cluster structure. Okay, so now I've sort of done the motivation, and then again I said I would really explain, even for people that don't know. Yes? They're just any fixed numbers, any fixed complex numbers. They can. Yeah. So thank you. Yeah. Of course. I mean for generic, let's say for generic A and B. Exactly. Yeah. Good. Yeah. That's important. Thank you. Yeah. So this is going to be this is the idea that there are very simple periodic dynamical systems, so Zamolodchikov periodic systems, and by inserting parameters, you can get systems which obviously reduce to that in the special cases of parameters, but for generic parameters, they will destroy Zamolodchikov. Yeah. So in fact, the condition is if B equals A squared, then everything, you can tick everything. So that's the condition here. Yeah. So now let's try and do a 5-minute introduction to cluster algebras, which is probably a bit foolhardy because you need a whole lecture course more or less. But anyway, what's the idea in a cluster algebra? I'm just gonna talk about coefficient-free cluster algebras, and so in a way, in the language of one of the talks today of Volin, then I'm sort of talking about T system relations rather than Y system relations. If you want to do Y systems, you have to have coefficients as well, but I'm just talking about coefficient free. So the idea is you start with something called a seed. So this is a seed is what generates a cluster algebra. So this is an n-tuple of variables or coordinates. And this is an integer matrix. Okay, so it's an integer matrix, and in the simplest case, it's just going to be skew. So I'll only show you skew examples today, and that means it also corresponds to a quiver Q, which doesn't have any. Let's draw self loops or two cycles. So we're not allowed to have a self loop from a vertex to itself, and we're not allowed to have two cycles. So these are forbidden. Okay. So how does you generate a cluster algebra? Well, you do what are called mutations. So the first thing is matrix mutations. So you start from B is your matrix, and you pick an index element. Or think of the quiver. Pick a node K, and then you do mutation mu K. So what does that do? Well, it produces a new matrix with entries Bij prime, which is given by minus Bij if I equals k or j equals k, and then it's given by a slightly more complicated formula. Otherwise, let's write it down, sorry, sine of Bik times the product of Bik, Bkj plus otherwise. So that's the first step in the cluster algebra is to do matrix mutations for a fixed k. So I call the mutations mu k, and that will produce, so that will start with my B, and that will produce a new matrix, let's say B prime, which is mu k of B, which has entries Bij prime. And that has also a nice interpretation of, in terms of the quiver, which I'll maybe show you a picture in a minute. And the other thing is the cluster mutations. So in the way the cluster mutations are kind of easier to describe, but so you take your tuple x, you apply the mutation mu k, and you get a new tuple mu k of x, a new n tuple where xj prime is equal to just equal to xj if j is not equal to k, and otherwise the formula is what's called the exchange relation, which is a product of xj bkj plus xj minus bjk plus. And I'm sorry, I didn't define this square bracket notation. I just mean that for any real number, this is the positive part. Okay, so that's this is what mutation is. And then the point is, for any seed that you start with, you have n different choices of directions to mutate, and you just you do all possible mutations in all possible directions. You you can keep doing that, and you may have to go on forever. And then the cluster algebra that you get from this seed is the Z algebra that's generated by all the cluster variables. So you start off with your x1 up to xn. That's your initial set of cluster variables, and it's you can just take any polynomials in those all of those cluster variables. And then, so the first result that follows from this definition is that all cluster variables are Laurent polynomials in the initial cluster variables with integer coefficients. And the second kind of important point here is to say, when are there finitely many? So if you like, the first theorem, if you like, is that all cluster variables belong to the ring of Laurent polynomials in the initial cluster. But in general, there may be infinitely many cluster variables. In general, there are. But When are there only finitely many cluster variables? Well, exactly when the matrix B comes from a Dynkin quiver, or a concatenation of Dynkin quivers. So essentially, the Dynkin classification of semi-simple Lie algebras corresponds in a certain sense to the, it gives you also the classification of finite type cluster algebras. Okay, so before I carry on, then I'll just mention a couple of examples. I'll write a couple of examples. So the first one is actually what we've already seen, is just A2. So we draw the A2 Dynkin diagram, we put an orientation, and that just gives us this matrix. And then we can think of the cluster variables sitting on the vertices. And then if we do x1, x2, well, we have a choice of where to mutate. We could do mutating here or mutating here. So let's do mu1. And what we get is x1 will be x1 prime, which will be exactly x3 in the recurrence relation that I calculated there, x2. And then, okay, if we keep on going, and the quiver, just all we do is reverse the arrow. All the arrows going in or out of the node where you mutate get reversed. So that's part of the rule in terms of the quiver. Now, of course, we could do mu1 again, but mutation is an involution. So if we did mu1 again, we just get back to where we started. So we want to do mu2. So now we mutate this, we change this one, we would get x3, and now x2 prime. If you follow through the definition, you'll find that that's actually x4 that we calculated from this recurrence relation. And then you can keep on going. And then, okay, so what we'll get next is x5, x4. And if we do a fifth mutation, we don't quite get back to where we started. We actually get so we get x5, x6, but x6 is x1. And then, so that's 4. And then finally, one more. We do mu1 again. We get x2, x1. So we almost got back to, we basically got the same cluster, but just the variables are in a different order, and also the orientation of the quiver finally will be reversed. So you need to do another 5 steps to get back where you started. Now, the next example to show quickly, and make sure that I don't run out of time. But this will illustrate the whole idea of the talk, essentially, is now, it seems like it's going to come out of nowhere. So this is a cluster algebra of rank 7. So there are 7 variables. Sorry, minus 1, 0, 1, 1, 0, minus 1. I'm just going to sort of fill it in, the entries that are easy to fill in. 1, 2, 3, 4, 5, 6. Yep. And then 0, 1, 0, minus 1. This is minus 1, 1, 1, 0. These ones are going to be easy to do, and the only one I need to think about is 1, 2, 3, 4, 5. So I have my matrix is looking non-square. Okay, so this one will be 0, 0, 1, 1, 0, minus 1. This one will be 0, minus 1, minus 1, 0, 1. And then in the middle, I want -1, 0, 1, 1. Okay, so that if I drew it right, that should be a square matrix, and the quiver that you get, I can save a bit of time. The quiver that you get looks like this. So and then okay, and that one like, okay, so you can check my drawing if I made a mistake. So what's missing? There's an arrow going across to 3. Okay, so it looks a bit messy. You can try and draw better. In fact, in 1 minute I'll turn on my slides and you'll see a properly drawn version. So what's special about this quiver? Well, this quiver is what I would call a special sum of 7 quiver, which was found in a paper of Fordy and Marsh. So one of the things about cluster algebras is that, in general, you don't get dynamical systems directly from cluster algebras, because your mutation possibilities give you a tree. So each time you start in one place, you have n different choices of which direction to go. A dynamical system, you just want to go in one direction. So what's special about this quiver is that it has period. It's what's called oh, this chalk is collapsing. It's called period 1. So if you do mutation at node 1, apply that to this matrix B, then what you'll find is that it's equivalent to a cyclic permutation. So my drawing looks a bit ugly, but what I'm trying to say, apply the mutation here. Well, one thing is that these arrows will reverse, but also all paths of length 2, which pass through node 1, will add arrows from the vertices in between. So example 4 to 1 to 2 will add an arrow in that direction, which will cancel the arrow between 2 and 4. Similarly, there's a path that goes from 4 to 1 to 7. That means that you need to add an arrow from 4 to 7, which will cancel this arrow. And okay, there's a couple more. There's 2 more paths. So there's a path here which will add an arrow between 5 and 7. And there's a path, there's one more path here between 5, 1, 2, which will add an arrow here. So if you look at this very carefully, you'll find that all that happens is the quiver rotates exactly. It's just a cyclic permutation of the vertices. So what that means is that if you do the exchange relation, you get x1 prime x1 is equal to, it will be, x2 x2 x7, and then plus x4 x5. Okay, so this is what's called a sum of 7 relation. And now if you keep doing, because it's a cyclic permutation, if you keep iterating 1, 2, 3, 4, 5, 6, 7, you'll get this recurrence relation. Xn plus 7 xn is equal to xn plus 6, xn plus 1, plus xn plus 4, xn plus 3. Okay, so this is what's called sum of 7 relation. Now, what does that have to do with anything else that I've been telling you? Well, if you know about singularity patterns of discrete dynamical systems, which is what the kind of naive version of Painlevé analysis for difference equations. So what the approach of Grammaticos Ramani, which was mentioned in Takanawa's talk, then the singularities of the Linnaeus you'll see that, so this map, the singularities go like, if you have a 0, then a regular point, then a simple pole, then a simple pole, then a regular value, then a 0. So this suggests, again, this is related to Paulin's talk, the T substitution in Y systems. If you say take for Linnaeus, if you take, let's call it this xn, and let's call it xn tilde xn plus 5 tilde xn plus 2 xn plus 3. Yeah. So now the zeros of x tilde will reproduce the singularity pattern of the xn that satisfies the Linnaeus map. And then what you find is that this xn tilde exactly satisfies SOMO 7, but with these coefficients a and b. So essentially, you have a hidden cluster structure of rank 7 with these are called frozen variables, so you can think of them as extra cluster variables that are fixed, they don't mutate. And that gives you the Linnaeus map. Okay, so this is the simple example. This is the motivation for the rest of the talk, and I know that I'm essentially out of time, but I can just show you some pictures of quivers for the last, do I have 2 minutes or? Yes? I have 3, even better. Okay. So well, I'm the last. I can say many nice things about the organizers and get extra time. So wait a sec. I need to kill. Oh no, it's not. Is it a touch screen? No. I just want to. I'll make it full screen. Yeah. Okay. So that slide is irrelevant. So here's yeah. Okay. If you look on the side, you can see the quiver. So this is a better drawing than I did on the board very quickly. This is the quiver that I drew of SOMO 7, but it has also those 2 frozen variables, which correspond to the coefficients. So yeah, look left or right if you want to see the picture. And then, so this is what you get from deforming A2 by putting in these parameters. You find that there's still a cluster structure. There's also there's a presymplectic structure for this, which pulls back to the canonical or log canonical symplectic structure in the plane that was for this Linnaeus map with A and B. So that's that example. Then just to show you very quickly in 1 minute that, I mean, this works for all Dynkin types as far as we believe. So A3 is interesting. It's in 3 dimensions. So you get a map in 3 dimensions. You put in some deformation. Here's the presymplectic form, and then which is the same in the deform. So the presymplectic form survives deformation. That's a basic result, a basic lemma. Then you can rescale, so you don't need to put in 6 parameters. You really only need 3 parameters. And then what you find is you say, well, when does the first integral that you had for the, now you want to reduce this map to the plane to talk about Liouville integrability. You reduce it to a symplectic map. So there's a null distribution. You quotient by the null distribution to get the log canonical symplectic form. And then what you find, well, the original map had period 3 in the plane, which is Coxeter number plus 2 divided by 3 when you reduce to the plane. And one of these Hamiltonians reduces by deformation to give you a new first integral h for your deformed map, which has two parameters, c and d. So that works. And then, okay, so this is the map that you get. You look at the singularity pattern. You can introduce two tau functions, and then this gives you a cluster map in 6 dimensions. You pull back the symplectic form to find the B matrix of the new cluster variable of the cluster algebra of rank 6, and then you extend it with two. So this is the quiver you get with two frozen variables. And then, yeah, okay, I pretty much will stop the talk, except that I'll just say that here's your extended cluster for A3, and you in fact find not only the tau functions for the deformed map, but you also find that there's another map which commutes with that map, and that is also generated by mutations in the same cluster algebra. So in fact, the story is that you have a family of elliptic surfaces of rank 2, and these two maps correspond to the two independent generators of the Mordell-Weil lattice. So actually you can define the tau functions on the two-dimensional, on Z2, on the Mordell-Weil lattice. And then there's many things you can do, so I'm not going to go through. This is just explaining how all the mutations work by linear equations. And finally, you can write down bilinear equations on Z2, and you can tropicalize to calculate degree growth if you're interested in that, and prove that the entropy is 0. And then you can calculate also the degree back in the plane in P2 and check that the entropy is 0, algebraic entropy is 0. And then, okay, this is to just show a picture. This is an orbit in 4 dimensions, which it projected into 3 dimensions and shown in 2 dimensions. So that should be a 2-dimensional Liouville torus of a 4-dimensional map, which is what you get from deforming A4. And the quiver looks horrible, but what the student Wu Qiang has done is incredible, because he's found a beautiful structure of this quiver. He redrew it, and now you see it has an asymmetry, and he's extended it to an infinite family in type A. So there's a nice substitution rule that you generate infinitely many quivers in type A, type A even. And then we've also done types B and D, and he's even generated infinite families now, which even are not all written in the thesis. Okay, so I'm sorry I probably run over time, but thank you very much for listening. If you want to applaud now, you're welcome to applaud and ask questions. And then I also, but also before that, I just want to thank the organizers, Anton and Bart and Ivan and any other organizers that I missed, for doing a wonderful job, creating a wonderful meeting, very great hospitality, lots of great talks. So thank you to the organizer and to all the other speakers. Okay. And then if you want to ask me some questions, you can, or
as an organizer.
As an organizer.
Are there any questions to Andrew?
Actually, I have a question about Laurent phenomena for the generalized
yes.
map. Yeah. Mm-hmm. As far as I know, so it comes from the special case for the Somos 7, yeah, and special case for the Somos 7 is some kind of special case of Gale-Robinson sequence.
Of Gale-Robinson, exactly.
Yeah, and well, there is a paper by Fomin Zelevinsky that even with arbitrary parameters, this sequence has Laurent phenomenon.
Yeah, exactly. So that's in the Fomin and Zelevinsky's Laurent phenomenon paper, where they use what's called the caterpillar lemma to prove Laurent property. In fact, the way that they do it is they start from the discrete Hirota equation, also the Hirota-Miwa, the type B as well, and they show that all of the reductions inherit the Laurent property from so that equation is a reduction of discrete Hirota. That's just if you want to talk about Laurent property. But then what Fordy and Marsh showed is that also you can construct a quiver for all of those Gale-Robinson. In fact, with Alan Fordy, we worked out quite a, that's why I was writing that matrix with ones and zeros, that we have a very simple algorithm starting from a Gale Robinson, we can construct the quiver. So and then, okay, other people like Okubo has shown actually like infinite quivers for discrete bilinear KdV and discrete Kp. So you can also even start from some infinite quiver for discrete Kp and maybe do some folding, but it's quite complicated to go down from infinite quiver of discrete Kp down to a one-dimensional current. So it's easier to the algorithm is very simple. You just start from the bilinear equation, and there's a rule to go from one line to the next. In fact, when the first time I met Zelevinsky, he said, "Oh yes, you're interested in these Somos sequences," and he wrote down Somos 4. Then he basically calculated the quiver just by hand in front of my eyes. And I had no idea at that time how he could do it. But then, a couple of years later, I worked out what the algorithm is. But yeah, but he just knew what to write down. So yeah.
Other questions?
Like if you take case 3, A4.
A4?
Well, let's say A4.
Yeah, let's say A4.
Which mutations you apply to make your time evolution?
Yeah. So A4, we start with. It kind of looks rather like. I mean, the A series all look similar. So you can just start with the quiver with all the arrows, pointing in one direction, and then you do mu1, mu2, mu3, mu4, and that produces a periodic map. So what is it? Is it, period 7, I guess? Is that right? Yeah, period 7. So that gives you a map in 4 dimensions. Then you look at the singularity pattern. So there are several singularity patterns, and you introduce tau functions. So you end up lifting it to a cluster algebra in dimension 11. So that's that quiver there on the left. It has 11 nodes and two plus 2 frozen ones, 12 and the one on the left at the top on the screen. Yeah, that's the A4. So there's a 2-parameter family. Essentially, you can introduce parameters into the 2 parameters into the mutations, and you can also there are some natural, again by averaging, there are some natural first integrals. There are 2 Poisson commuting ones, and you can deform them to this system. Yeah.
So my question is as follows. It's known that pentagon and solutions to pentagon give rise to invariance of manifolds. And, recently it was discovered that it gives rise to invariance of braids very differently.
Yeah.
And I wonder whether these ways of upgrading cluster algebras and upgrading pentagon to heptagon or whatever, whether they may upgrade any invariance one can get from cluster algebras.
Okay, that's a very interesting question. The one thing is that in the if you look at, there's something about the pentagon relation which is sort of fundamental. We saw it in the first talk this morning. So Nakanishi has a paper about dilogarithm identities and pentagon, basically, and how basically all of the cluster mutations in general give you functional identities for the dilogarithm. They give you, but all of those identities are consequences of the pentagon relation and some elementary symmetries. So I think at the moment these things are just, they're still just there. Once you've upgraded them, let's say there's still a cluster algebra sitting above. So so that's why I'm saying I'm very cautious to say that there's anything new in terms of invariance. But if there are, it would be great. Thank you. Yeah, thank you for the question. Yeah.
Other questions? Okay, so let's thank Andy again.